In previous videos we looked at the differential equation that models the motion of an oscillating mass. This term here is the damping term. This is the damping force on the mass. It's in a direction that is opposite the velocity of the mass. So if the velocity is, say, up the way, then the damping force will be down the way. The magnitude of the damping force depends on k. If we double k, we double the damping force. So as k goes up, the damping force goes up. So the larger k is, the more quickly the mass will die down to its equilibrium position. Here is the auxiliary equation that goes with the differential equation. We use the letter lambda instead of k because k is already taken up as the damping coefficient. We solve for lambda and well, we can then form the solutions of this differential equation. The types of solutions that we get for this differential equation depend on the nature of the roots of the auxiliary equation. So the nature of lambda depends on this thing called the discriminant that's inside the square root sign. If the discriminant is less than 0, in other words if k squared is less than 4mn, then we have a situation of light damping. So k is relatively small. If the discriminant is equal to 0, in other words k squared equals 4mn, k has now increased. We have what's called critical damping. So we have greater damping in this situation. And finally, if the discriminant is greater than 0, in other words k squared is greater than 4mn, so k is even greater now, we have heavy damping. In this video we are going to deal with heavy damping. If k squared is greater than 4mn, then the discriminant is positive. We'll have two distinct real roots. So here are the two roots. We just take the plus sign for one root and the minus sign for the other root. We can call them lambda 1 and lambda 2. So we have two distinct real roots. We have the square root of a positive quantity here. And we saw in a previous video that the general solution of the homogeneous differential equation with two distinct roots of the auxiliary equation is given by this here. So we can apply that here. Well, in this situation the dependent variable is x and the independent variable is t. If m equals 1, n equals 1 and k equals 2.5, find lambda 1 and lambda 2 and then find the solution for the displacement x. So we just plug these numbers into each of these and we can get our two values for our two roots, and then we just plug those values in here for lambda 1 and lambda 2. Next we will apply these initial conditions. So the initial displacement vector is x sub 0 and the initial velocity is 0. So we will have to get dx dt. We'll have to differentiate this, and that's straightforward. Here's the derivative, and at t equals 0 the derivative is 0, so we plug 0 in, so we get 0.5 minus 0.5a minus 2b equals 0, and the position vector is x0. So if we just plug 0 in for t here, we get a plus b equals x sub 0, the initial position vector. So we can get a and b in terms of x0. From this equation here we get a equals minus 4b. And if we plug minus 4b in for a here, we get x0 equals minus 3b, or b equals minus a third x0. And if we add a and b together, we must get x0. So minus a third plus 4/3 gives us 1 x0. Next we plug what we got for a and b into this here. Gives us the displacement vector, and you can see that a third x0 is a common factor because we've 4/3 x0 in front of this, and we've minus 1/3 x0 for b in front of this exponential term. Right, these powers are both negative, of course, so that means as t gets large, both of these terms will die to 0. At t equals 0, the initial value is x0. Notice also that the slope of the curve at t equals 0 is 0. We have a horizontal tangent to the curve at t equals 0.